Okay, we should start. So let's start the second session of Fair Data Management, and we'll start with who, how.
Thank you. Good morning, everyone. My name is Hu Hao, and I'm very glad to be here and give the talk about DOMAS, a data management software framework for advanced light sources. And I come from HAP Computing Center, and I'm also a member from HAP's Computing Center. This is the outline of my talk. First, I will give a brief introduction about light sources in China. So far, we have 12 light sources in China, facility in China. And in the north, we can see here, most of them are located in Dalian and Beijing. And in the east, there are 4 facilities in Shanghai and 2 in Hefei. And in the south, we will have 2 light sources in Shenzhen and Dongguan. Most of these facilities are already in operation, but some of them are still under construction. So you can see here HAPS, high energy photon source, and SHINE. Shanghai hard exfil will be finished in 2025, and HAF and Hefei advanced light source has just been already approved and will be finished in 2028. And Southern advanced photon source is being proposed to construct. So from this map, we can see that China is currently experiencing a rapid development phase for advanced light sources. So these advanced light sources use many new technologies. So it will produce huge data volume even at the exabyte level. So here you can see HAPS will produce over 300 terabyte raw data per year, and SHINE, which is an exfil facility, will produce 5 exabyte raw data per year. So this huge amount of data is a big challenge for data management and processing. So we designed a full lifecycle software system to provide the full chain and full lifecycle and automatic service for users from the proposal to the experiment and to the data analysis. So here it consists with 3 software framework, control and data acquisition software member, data analysis software framework DAISY, and the data management software DOMAS. So here we can see the DOMAS is the essential component and provide the interfaces for the data access. And 2 of my colleagues, Hu Yu and Zhang Yi, have 2 posters about DAISY and Mamba. Then I will go back to the requirements of data management system. First, we need to design metadata model and design a metadata database and provide different interfaces to access data and metadata. Then we need to acquire metadata from other different subsystems, such as DAQ, transfer, storage, and so on. And then we also need a transfer system to move data automatically between different storage devices. Because we designed multiple layer storage. And at last, we also want to provide a data service to give interfaces for users to search, access, and download and analysis data. So this slide shows the architecture of DOMAS. Here, DOMAS has 4 core functional modules: metadata catalog, metadata acquisition, and data transfer, and data service. And it is a decoupling design and the extensible and standard interface. So by using DOMAS, here, this is DOMAS. So by using DOMAS, you can build a data management system for light sources or beamlines according to their requirements very quickly, and just by some configuration or the low-code development. So first, I will introduce the most important function module, metadata catalog. It is responsible for storing metadata into database and provide APIs to access metadata. Here we use the MongoDB as a backend database, and because the metadata is very complicated. And then we developed a tool to generate RESTful APIs to automatically from the metadata models. So here, the interface developers can design a metadata model from the web GUI and create APIs from the GUI. And then all the metadata models and the interfaces can be parsed, verified, and processed in the backend. And then other systems or modules can revoke the APIs from this system. And this slide shows the which metadata items we need to be cataloged and where does this metadata come from. But here we just focus on where this metadata from. Here we can see these metadata from very different system and databases. So here, we design a very extensible architecture to acquire metadata from different systems or databases. And the Kafka cluster here, used here can acquire metadata from different sources, such as Epix or Tango DAQ or Mamba DAQ, or from the data transfer. And so here we can know which data files are produced from these detectors. And then this metadata also can be enriched by supplement some information from the user database, proposal database, and the sample database. And here we also developed several metadata ingesters. Here, for example, we can ingest experimental environment metadata from data files here. So ingest plugins is very flexible, developed, and can be very flexible to deploy. So at the end, all the metadata can be cataloged here. So next is about the data transfer. Data transfer support cluster deployment. It has one control node and could have several transfer nodes, which depends on how much data you want to transfer. So in the control node, we can see a very useful and highlight feature, transfer task discovery. And for this module, can find out which data set need to be transferred by data pooling or the directory monitoring. And in the transfer nodes, we support a lot of transfer protocols, such as rsync, SCP, SRU DCP, EOSCP, and so on. And we can also integrate other transfer protocols, even the commercial protocols. And we know it's a universal data transfer software, and it is used in other high-energy physics experiments, such as Juno and LASSO. For the data service, first we design a specialized computer terminal, which placed at the user center and the user lounge. It is suitable for downloading huge volume of data, so we can support different storage device interfaces. And second, we designed a data web portal for users to search, download, access, and analysis data. And here we also developed a web browser for the data, so a user can browse their data from the storage, just like they are using their own computers. And we integrate a client for the data downloading, so it can greatly improve the download speed and maximize the utilization of network bandwidth. So here we can see the utilization of network bandwidth can up to more than 80%. So now DOMAS has been released and are being open sourced progressively. And now we have open sourced 3 modules of it. And first we apply DOMAS to HAPS, and HAPS data management system is now can stably running in the production. And then we also apply to DOMAS to other facilities, such as other light source, BSRF, and the neutron source, CSNS, and the astro particle physics facilities, such as HERT. So that's the summary and plan. And DOMAS is developed to make data fair and will be open source progressively. And DOMAS has been applied to some light source facilities, neutron source, and astro particle physics facility. And next, we will promote the application of DOMAS at SHINE and HUF. And we still keep on operating with the other light source facilities and communities. Okay, that's it. Thank you.
Thank you very much. We have room for one question, if any. I've got one, a small one. I've seen that you are considering to provide users with a web application where they can configure themselves the model for their metadata. The web application where everything can be configured for the models. Does it mean that each user can modelize the metadata the way he wants? There is no uniform way of...
We provide services to beamlines or to the light sources.
Mm-hmm.
Can design their metadata model. And
Each user can...
No, not all the users.
Okay. Thank you. So, floor is... Thank you very much. Yeah, it's here.